Hello friends, this video on structure of atom part 35 is brought to you by examfear.com. No more fear from exam. Before watching this video, please make sure that you have watched part 1 to part 34. Now we'll study the electronic configuration of atom. What is electronic configuration? The distribution of electrons into orbitals of an atom is called electronic configuration, where we'll tell how the electron is distributed across various orbitals in an atom. Right? And the electronic configuration can be represented in two ways. One is SPDF notation, where you say S subshell has this many electrons, P subshell has this many, D subshell has this many electrons. Or you can create the orbital diagram. You can say S subshells, P subshells with 3 orbitals, D subshells with 5 orbitals. Like that you can create the orbital diagram, or you can use this notation. This is generally used because it is easy to create than to write so many boxes. So this is more in fashion, little easy, but we'll understand both these. Both are same actually. In both represent same data. The only thing is the representation is different. But there is an advantage of second over the first because it represents all quantum number. So this guy will not represent all the quantum number, but this will represent all the quantum number. Looking at this, you can tell the quantum number for all the electrons. We'll discuss more in detail for that. So we'll write some electronic configuration for hydrogen, let's suppose. So we'll write the first way. For hydrogen has how many electrons? 1. So if you see, let me write in that first box. So this is my s orbital, which can have at the max 2 electrons. But there is only one electron here. It will occupy position like this. This is the orbital representation, or I can write the same thing as this fashion also, 1s1, because the first s will have 1 electron. Hope you understand. Let's take helium now. Helium has 2 electrons, right? So if you write in this box, this is the first s subshell, this is the s subshell, right? 1s subshell. So the first electron will come and the second electron will be paired, and this is my helium. Also, I can write helium as 1s2. Both are correct, right? This is the orbital representation and this is my normal representation. Let's see for lithium. Lithium has 3 electrons. So let's write the orbital first. So orbital, I'll have first 1s orbital. Then the next energy is 2s orbital. Correct? The first electron comes, it comes in this 1s orbital. The second comes, it pairs up. The third comes, it comes in this orbital. So this is my orbital representation for lithium. And the same thing I can write in the normal notation. 1s will have 2 electrons and 2s will have 1 electron. This is also one representation. Correct? Let's see for barium. So barium has 4 electrons. Right? So I have my 1s subshell. I have my 2s subshells. First electron comes here, it sits here. Second will pair up. Third will come here. Fourth will pair up. So this is my orbital representation. If you want, I can write in this fashion also 1s2, because 1s subshell has 2 electrons, and 2s2 because 2s subshell has 2 electrons. Then the boron. Boron has how many electrons? 5 electrons. Correct? So we have to accommodate in 1s. Then I have 2s. 1s can take 2, 2s can take 2, but it will not be sufficient. So I have something called 2p also, right? And 2p will have 3 boxes because p subshells has 3 orbitals. So let's start with the electrons. First electron will come here. Second will pair up. Third will come 2s because the next energy level. Fourth will come here. Fifth electron will come in 2p orbital, right? Because it is in the order of increasing energy level. This is the orbital representation. I can also write this guy in 1s has how many electrons? 2 electrons. 2s has how many electrons? 2 electrons. 2p has how many? 1 electron. So this I can write in this fashion also. Let's take carbon. Carbon has 6 electrons. Same thing I can write. Let me write the first box form. So this is my box. This is my 1s orbital. Then I have 2s orbital. And then the next orbital is 2p1. I am writing in the form of increasing order of energy. So this is this 2p1 will have 3 orbitals, right? These are 1s subcells, 2s subcells, 2p subcells. So this 2p subcells will have 3 orbitals. So I wrote 3 orbitals. 6 electrons, first will come to 1s, the lowest energy. Second will pair in this. Third electron will come in the second second lowest energy subshell. Fourth will obviously pair. Fifth will come here, and sixth electron should come here or here. So according to Hund's law of maximum multiplicity, this guy won't start pairing until all the orbitals are filled with 1 electron. So this guy will come here. I can also write this guy as 1s has how many electrons? 2 electrons. 2s has how many electrons? 2 electrons. And 2p has how many electrons? 2 electrons. So both are correct. But this gives a clear picture. This gives a actual place where the electrons are, right? Let's take for nitrogen. Nitrogen has 7 electrons. So I know that 1s, then I have 2s, then I have 2p. This is my increasing order of energy for orbitals. This is I know, right? So I'll write 1s box here, 1s shell. These are all my subshell actually, subshells. 1s subshells, then I have 2s subshell, and then I have 2p subshell. 2p subshell will have 3 orbitals, so I drew 3 boxes inside this. 7 electrons, the first comes here, second comes here, third comes here, fourth comes here. This is I've seen. Fifth comes here, sixth again, it can come here or here, but according to Hund's law of maximum multiplicity, it should come here. Seventh, where it should come? It can come here, here, but no, according to Hund's law of maximum multiplicity, it should come here because the pairing should not start until all the orbitals has 1 electron. So this is my electronic configuration. I can also write this as 1s with 2 electrons, 2s subshell with 2 electrons, and 2p subshell with 3 electrons. And that is it. Please note 1s, 2s, 2p are all subshells. They are all subshells. They are not orbitals. Now 2px, 2py, 2pz, these are all orbitals. Correct? So this p subshell has 3 orbitals. S subshell has 1 orbital. Let's take for oxygen. Oxygen has 8 electrons. Correct? So again I have 1s subshell, lowest energy. Then I have 2s subshell, then I have 2p subshells in the order of increasing order of energy. So let's write 1s subshell. It will have 2 electrons. 2s subshells, then I have 2p subshells. 2p subshell will have 3 orbitals. So I drew 3 boxes. 8 electrons has to come. First will come here, second will come here, third will come here, fourth will come here, fifth will come here. According to Hund's law of maximum multiplicity, 6th will come here, 7th will come here. Now 8th will come where? 8th will come here. Why? Because each of these orbitals in p has got 1 electron, so the pairing will start now. So I can write this guy also as 1s2, 2s subshell has how many electrons? 2, and 2p subshell has how many electrons? 4. I can write in this fashion also. So both are correct. Let's take for fluorine. Fluorine has 9 electrons. Correct. So again my 1s subshell, then I have 2s subshell, then I have 2p subshells in the order of increasing order of energy. So I'll write here once again. I'm taking more examples so that you can understand the concepts and write electronic configuration easily. It comes out of an exam. So this I have 1s subshell, then I have 2s subshell, 2p subshell will have 3 orbitals, px, py, pz. 9 electrons, first will come here, second will come here, third, fourth, fifth, sixth, seventh. 8 we saw it will come here, so 9th will come here. This is how it will be. So it will be 1s subshell has 2 electron, 2s subshell will have 2 electron, and 2p subshell will have 5 electron. That is my fluorine. Let's take neon now. Neon has 10 electrons. Correct? Atomic number is 10. So again I have 1s, 2s, and 2p in the order of increasing order of subshells. So let's draw 1s. Let's draw 2s subshell, and let's draw 2p subshell. 2p subshell will have 3 orbitals, so I drew 3 orbitals. First electron comes here, second comes here, third, fourth, fifth, sixth, seventh, eighth will come here, ninth will come here, and 10th will come here. So you see all the orbitals are filled in this case, and that's why neon is noble gas. It is very, very stable. Correct. Now we'll see some simplified electronic configuration. So if you see the electronic configuration of sodium, if you do that, if you try to find electronic configuration of sodium, you'll find it comes out to be like this: 1s2, 2s2, 2p6, 3s1. Correct? Because after neon we have sodium only, you can do that. So still this is neon, then we have sodium. And if you see argon, it comes like this: 1s2, 2s2, 2p6, 3s2, 3p6. So if you see, this part is common in both cases, right? This part 1s2, 2s2 and 2p6. Please note, this part is common to any of the element from sodium to argon. You just write the electronic configuration, you will see that this part is common, right? They have exactly the same pattern. The only difference is here first 3s get filled, and then here after 3s 3p gets filled, right? Because there are 8 elements in that series. So this is the pattern. So we can simplify this process. How? Instead of writing this big name, because this configuration corresponds to what? Neon, right? If you see 10 electrons, so we can write neon instead of this big 1s2, 2s2, 2p6. See, now it is not that big deal because here we have only 1, 2, 3, 4 subcells here. But if you write the electronic configuration of higher atomic number elements, the electronic configuration will be very big. So in that case, it helps where you can shorten this thing with, here in this case, neon. Because each of these will have this. For example, sodium I can write as neon 3s1. That is nothing but 1s2, 2s2, 2p6, 3s1. Argon I can write as neon 3s2, 2p6. That is nothing but neon you can replace with 1s2, 2s2, 2p6, and then you can write it. So this makes the life simple for chemist, right? Also, the electrons in the completely filled shells are called core electrons. They are called core electrons in the completely filled shells. And the electrons that are added to the electronic cell with the highest principal quantum number is called valence electron. That means the last orbit which you have, the electrons in the outermost orbit is called valence electron, and they are easily to pluck. So if you give some ionization energy in that, they are the one who comes out first. So the electrons in the outermost shell of the atom is called valence electrons. Thank you. Visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thanks once again.